Welcome back. We got some geometry going on here. Chapter 10, lesson 2. We're going to split this again into two parts, 2A, 2B. This is more of a vocabulary portion, and we'll get into some nitty-gritty doing some assignments. So they're a little shorter that way. After this, we've only got one more lesson. I mean, this is A and B is one lesson, even though it's two videos. And then we'll do one more, and then we're done for the year. Awesome. Good job, folks. With it. Cavalieri's principle. If you didn't know how to pronounce that, it's Cavalieri. It's just like Cleveland Cavaliers. Okay. I want to say something about LeBron, but you. Okay. Look, Cavalieri's principle in 2 dimensions. Okay. It is. We use it in 3 dimensions for the most part, but in 2 dimensions is how we set that. If 2 figures have the same height and the same width at every point along that height, then they create the same area. Okay, what that just means is like we talked about in the last video. It's like a stack of Ritz crackers. If you got a stack of Ritz crackers, and just because I take those Ritz crackers and I make them just off like 1 millimeter on each stack of each one, they're still the same volume because there's still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Okay, that's why I didn't think I got it right. There's still 12 Ritz crackers here. There's still 12 Ritz crackers there. Now, the key idea is that 2 figures have the same height and width at the width is at every single point. Okay, and that's where they try and trick you a little bit. Okay, this has the same width. Okay, this has 4. It's 4 here. It's 4 here. It's 4 here. It's 4 here. Just like this picture. Okay. That gives us 4 times 6, an area of 24. So what is the area of the rectangle? What is the area of parallelogram? They're both 24. Now, we've dealt with that before, because also what I could do is I could cut this triangle, and I could rotate it around right there, and I would then have that thing coming off right here. This would kind of disappear, and really what I've got is now the same area again. Okay? Hopefully that makes sense. Moving on. Here's where they try and trick you, because it seems is right. Sometimes a figure has different widths at different heights. Okay. According to Cavalieri's principle, which of the following must have the same area? This is 3. This is 5. This is 3. This is 5. Now, at this width and this width, maybe it's 2.5. Maybe this is 2. Maybe this is 1.5. Maybe this is 1, and then back to a 0. Obviously, I didn't do it at a uniform rate. The problem with that is this drops maybe a half. This doesn't seem to have dropped very much. And this drops down another half. This doesn't seem to have dropped very much. I would, venture to say, yeah, it's about the same size as this. At the same height, this is not the same width as these two are. Definitely not the same width right here. It's way bigger. So these two, A and B, are the ones that have the same width at all of the corresponding heights. 1 inch off the ground, 2 inches off the ground, whatever. All right, and here's a little bit more of a 3D looking at that. Just like with the Ritz crackers, they use poker chips. It doesn't matter if they weave around. Now, you could talk physics on that, and you could realize that. I'm going to do something here real quick. Oops, I didn't want to do that. So we'll erase it. What I do want to do is I pushed on the TV probably a little too hard, so I want to turn some of those pixels back on. Yikes. Hopefully I didn't break it. Anyway, the one thing that is true is you'll realize in physics is that they all have to have a portion of their center of gravity over the same, this one can't be outside of this one, but another day. Same deal, 2 3D figures, okay, same width at every single place. Now, if the actual area of this circle was, let's say, 3 pi, and the area of this square was 3 pi, and the area of that circle was 3 pi, and the area of that square was 3 pi. And then halfway up, it was still 3 pi, 3 pi, 3 pi, 3 pi. And yes, you can have 3 pi for an area of a rectangle. There's no point in it, but you can. And then 3 pi, 3 pi, 3 pi, 3 pi, and these were all 2 inches tall. These would all have the same volume. Okay, so if the area of the base and the area of each cross section at the same height, then they will have the same volume. Okay, see cross-sectional area. I just said cross-section. Cross-section generally refers to a 2D situation. So cross-sectional area is probably the better way of saying it. And it's just like a stack of coins or books or playing cards. I like Ritz crackers because then when you're done, you can eat them. But anyway. Following figures have the same height and the same base area. Which of the following ones have the same volume? Okay. So this same height, they all go across. Whoa, I didn't want to do that this time. Let's go right here. They have all the same height. If I was able to draw that perfectly and line them up perfectly. So let's do that. Let's move that up. Move that one up. There we go. Okay. They all have the same height. And this is the same. Again, we could just say 25, 25, and 25. Now, we haven't talked. Well, yes, we did. No, we did. In the last video, we did talk about it. That it's 1/3. Area of the base times the height, 1/3. Area of the base times the height, 1/3. Area of the base times the height, 1/3 for a cone and for a pyramid. So yeah, they all three have the same volume. Same volume, same volume. Next one I think is not quite the case. Now, one thing I tried to do on this is a little bit of trickeration. Sometimes they do it like this, and they remind you that this is the base. Okay? On a pyramid, anything that's not a triangle is your base. This is a triangle, but all three of these are kind of similar triangles, and so this is the different triangle, and so it's the base. And we can assume that this is probably an equilateral triangle. Pyramid is a collection of all points inclusive between a polygonal shaped, I would say maybe is a better way of saying it, base and an apex that is different or in a different plane from the base. Okay? Well, what I want to do on this is I want to look at this and actually rotate it. That's interesting that it doesn't show up. I have a little thing that's showing up around my iPad here as I'm moving it. That's weird. Oops. And I'm going to move this like that. Yes, I know I didn't cover that up, but it just gives you a little bit better perspective and helps you remember that that's the base. Okay? What are pyramids and cones? And maybe we didn't go over it last video. When I make these PowerPoints, these presentations ahead of time, I was like, where are we in the whole thing? But you'll find out as we go, and I'll correct what I said earlier if need be. Another way to think of a pyramid is a collection of all the dilations. So if you took this base and I scaled it 90%, 90%, 90%, 90%, 90%. Now, technically, we'd never get to 0. But maybe this is 90% of the base, then this is 80% of the base, and then 70, 60, 50, 40, 30, 20, 10, and then 0% of the base. Okay? So we've shrunk, if this started off with 10, the next one would be at 9, and then 8, 7, 6, 5, 4, 3, 2, 1, 0. Same thing here. If this was 20, and we went all the way up to 0. That's what it is. It's a collection of, and you have to think about it as, well, that's only really like a parking garage. It's just got levels. Boy. Anyway, I want to go with somewhere. Anyway, no, it's every single infinite space in between each of those theoretical levels that you're able to push on it. Okay, this is not the only space between here and here. There's one that's, here. There's infinitely many between here and here, which means there's also infinitely many on the way up. Okay, so cones. A cone, common pyramid-like figure. Again, same thing. Each circle is maybe 90%, 80%, 70, 60, 50, 40, 30, all the way to 0. All the way to 0. Okay, volume. I guess we didn't talk about volume. And it's kind of cool. There's a graphic, a GIF that they have on Khan Academy where it takes this, and I screen grabbed it right here, this being the cube. And what it did is it drew a line and it cut it from upper right back to lower left front. So I'll just draw that line for you. That line right there. They cut it right there, and then they cut it one other way. Anyway, it was really cool how they cut it. And then what it does is it rotates that section out to here, and it rotates that section out to there. And so what you find is you have three identical little pyramids inside of a cube, meaning one pyramid with this same base, same base, same base, and same height is 1/3 of what the cube that would surround it would be. Another way to try it in real life is to take a cone, well, it could be a cone and a cylinder. You can do this, and we'll talk about that in a second. But you could take a cube and a pyramid. Take the pyramid, flip it upside down, just flip it upside down, fill it with water. Pour it into the cube. Okay, fill it up with water again, pour it into the cube. Fill it up with water again, pour it into the cube, and it will level off right at the top. Okay, it's more of a practical, oh yeah, I see, I get it, I can touch it application. So the volume of a pyramid is 1/3 the area of the base times the height. And we have that up here on the wall. It's been up there all year. You can look at that. Good way for you to test yourself. All right, so the following pyramid is a scaled version of the previous square-based pyramid using different scale factors. Square-based, and then they give you a rectangle. That's a little frustrating, but at the same time, get over it. It's COVID. You know, we just have to deal with everything. So the area of this base is just going to be length times width, base times height, 6 times 2. All right, then, why is that way? It's weird. What I'm going to do is kind of remove that. Yeah, there we go. And what we end up getting here is we're able to take the 3, cancel out with the 6, and get a 1 and a 2. So I end up with 2 times 7.5. So the area of the base, well, the area of the base is 6 times 2, times the height, which is 7.5, is going to be 15. And I wonder if I have another one there. Oh, I forgot about that 2 as well. I'm like, 2 times 7.5 is 15. Oh, and another 2 gives us 30 centimeters cubed. And that's something we want to pay attention to as well. My scale is off on this. It's weird. I'm going to try and move these over. There we go. I think I can do that. Yeah. Centimeters squared. I made a mistake. Ha! It's centimeters cubed. So let's write that in there. Make sure we get the M and the 3. There we go, centimeters cubed. I put centimeters squared, and that's what you got to pay attention. I'm dealing with 3 dimensions, 3D, so cubed. 2 dimensions, 2D, squared. Area, square area, area squared. And then linear measurements are 1 dimension, so you've got just centimeters to the 1. You don't have to put to the 1. And that's introducing Cavalieri's principle, and then in the next video, we will spend some time working on how to just apply those in some of the questions that Khan Academy asks. Have a good day.